In the fourth experiment of the tutorial 5, we have 3 phonocardiogram signals PCG or PEC1, PEC33, PEC52. Okay, 3 phonocardiogram signals are there. Each one of them, they are 3 channel recording. The first one is PCG, second is ECG and third one is carotid pulse signal. And all of these signals, they are sampled at 1 kilohertz, and we are provided the MATLAB file to read it, that plot_peg.m. The signal in peg1.dat and peg52.dat, they are normal, whereas that peg33.dat, it is suffering from systolic murmur, and the patient suspected with pulmonary stenosis, ventricular septal defect and pulmonary hypertension. Okay. If you recall that we have gone through these phonocardiogram signals earlier in the experiment, and here our job is to appreciate that how PhD can help to differentiate this abnormal signal PEC33 from the other two, that is PEC52 and PEC1. And how we can do that? That for that we have to compute the PhD first of all, and then we from the PhD we can get the mean frequency. We can also compute the ratio of the energy in the range 100 to that in between 100 to 300 hertz in this bandwidth compared to the total energy of the PhD. Okay. So, fractional energy within this band, okay. And we have to comment that what can we infer from these measures. That means, whether these measures, that is mean frequency and the ratio of energy in the band, can help us to differentiate the normal signals versus abnormal signal. Okay. So, that is the task given here. So, we proceed with that. First we download the signals and that MATLAB file plot_peg.m, what is required to read those files, and we keep them in the working directory of MATLAB. Okay. Now, first thing is to input that signal and first appreciate that by seeing that plot. So, for that first we take that the signal PEC1.dat, we load that in the variable PEC, and we know that in the 3 channel signal the first channel is the PCG signal. So, we take that for further analysis. We take the samples from 801 to 23,000. We remove some part at the beginning to avoid some noisy samples, okay. And then we compute that what is the length of the signal, and that we can create the corresponding time axis here using that number of samples and the sampling frequency, and then we plot that signal, that PCG, with respect to the time. Okay. So, let us see how that signal looks like. Here we get the PCG signal. Okay. In the time domain, whatever we get, I think we cannot infer much out of it. It looks like a lot of impulses and noise mingled together. Now, next we go for the PSD. So, for that what we have to do? We have to first take the Fourier transform of the signal, then we need to take the energy. So, for that we have to take the absolute value and the square of it, and then we create the frequency axis and we take the plot of the PSD in the dB scale. And as it is given that they are sampled from 0 to that it is 1 kilohertz, that means we get the signal from minus 500 to plus 500. So, we concentrate on the positive part of it, that is 0 to 500. Okay. We limit that to get a better view of the signal. Okay. So, here we see the spectrum, and then we also calculate the energy, how much energy is there between 100 and that 300 hertz. Okay. Within this range, how much actually that energy is there, we simply sum it up, and with that we also calculate the total energy. So, we can take the ratio of the two. The ratio is given as that 0.017. It is a very small number, or we can say 1.7% energy is only there, okay, within this range. The range is 100 to 300. Actually, most of the energy, if we look at, it is concentrated in this part, less than 100 hertz in this signal. Okay. And this is the signal that PC 1 we are talking about here. Now, we go for the next task. We need to find out the mean frequency, and we know the formula, we have used it earlier. So, we compute the mean frequency and show the plot of it. Okay. Mean frequency is at 54.55. Please keep in mind, we have the spectrum 0 to 500, out of which we have taken the only the small part, that is of our signal of interest, that we are just looking into up to 100 here. So, that we can appreciate that this part better, but the span of the energy is from 0 to 500 hertz. Okay. But compared to that, the mean frequency is pretty low, it is lower 1/10 we can say, that part the mean frequency is located. Now, let us go for the other signals to appreciate that how the spectrum and the mean frequency they change, and along with the spectrum how the energy of the spectrum within the band 100 to 300 also will change. Okay. So, we compute that all these variable for peak 33 and PEG 52. So, here is the PEG 33. It looks like that it has more jagged or more random. However, that such visual measurements could be often wrong. So, let us not comment about it anymore. Let us look at the other parameters. What we get, that we get the spectrum. Here also we get the basic nature is there same, that most of the energy is below 100 hertz, we can say, like the previous signal. Okay. However, the probably that little more energy is there between 100 to 300, because what we get the energy ratio is 0.126, that means 12.6% energy of the total energy is here. Okay. In the previous case it was about 1.7%. Okay. So, an order of magnitude change. And if we compute the mean frequency for PEC 33, we get the mean frequency we get at a little higher frequency, that is 75.75 hertz. Okay. So, it is little higher than the previous case, which was around 50 hertz in the previous case. Now, we go for the other normal signal, that is PEC 52, and the corresponding the PSD we get here. Again the nature is same, in the sense that most of the energy is concentrated below 100 hertz or in this band, and when we look at the energy between 100 and 300 hertz, that we have the ratio with respect to the total energy is pretty small. We have that 0.0413, that means 4.13% energy is there. Okay. And now, if we look at the mean frequency, we get the mean frequency is lower than PEC 33, it is 66.73, but it is little more than that of that PEC 1. Okay. So, now as we have seen the PSD, the energy ratio and the mean frequency, now we go for the conclusion. First we state that what are that energy ratios we get here for the normal patients PEC 1 and PEC 52, we get the ratio of the energy between 100 and 300 hertz. It is 0.017 and 0.0413, that is 1.7% and 4.13%, and the mean frequencies are 54.55 and 66.73. So, what we get among the normal patients, there is some variation, it is not always remaining the same. And now, when we go for the disease subject and the PEC corresponding to that PEC 33, the ratio of the energy in the band 100 to 300 hertz, we get the total energy is 0.126 and the mean frequency is that 75.75. So, from this what we can get, that the ratio of the energy and the mean frequency both are more when it is a pathogenic case, because clearly the energy when we get, it is 12.6% energy is there, which is order of magnitude higher than the normal cases. Okay. So, both the mean frequency as well as the energy ratio taking the band 100 to 300 would be a good measure, and out of these two features, the ratio of the energy is giving better separation. Okay. So, it would be a better feature for classification of that pathogenic signal from the normal one. Thank you.